All right, on to triple integrals. This is a challenge that everybody, including me, needs work at, right? So we try to keep our examples relatively simple. When do you ever need to do triple integrals? Well, I was a physics minor. I don't remember actually doing many of them, but I do remember seeing them in some books. One place where you could do triple integrals is actually finding center of mass for a three-dimensional solid, a true three-dimensional solid instead of a thin lamina, a thin plate. You could have a density function that depends on x, y, and z. Still integrate that density function, you're going to get the mass of the solid now. The density function is a volume density function, grams per cubic centimeter, say. And you can also find the center of mass. You can find moments, not with respect to axes, but with respect to planes, like the xy plane, or the xz plane, or the yz plane. By doing appropriate integrals, and those can help you figure out the center of mass. And the formulas are in this section, section 13.6. But actually setting up these integrals correctly is very tricky. Let's look at number 9 here, just work through some problems. A domain D is described by its bounding surfaces along with a graph. Set up triple integrals that give the volume in all 6 orders of integration. Find the volume by evaluating the indicated triple integral. So the region, the solid looks like this. You're not always given a picture. It's certainly much nicer when you have a picture because it's hard to draw pictures by hand. And you can get Mathematica to draw these things, but it's still a bit tricky. That's what the solid looks like. It's bounded by the coordinate planes, which means, first of all, the xy plane, where z is 0, that's the bottom here. The xz plane is effectively the plane of the paper. And the yz plane is coming out of the paper a bit, like this way. So it's bounded by those, and it's also bounded by the graph of that function of x and y, which is a plane, a slanted plane. A little bit of review. If I asked you to find a normal vector for this plane, you'd want to subtract z from both sides and look at the coefficients of x, y, and z. -1/3, -2/3, -2, -1 after subtracting z would be a normal vector. It would point into the paper because all the components would be negative. Its opposite would point out of the paper. So we're trying to set up the integral with respect to all the possible orders, though only evaluate it with respect to that order. Maybe we should try to set it up with respect to that order first. Another thing that's a little funny at first is we're trying to find a volume. Wait a minute. Isn't it double integrals that give us volume instead of triple integrals? Shouldn't triple integrals give us hypervolume? Yes and no. If you do a triple integral of the function 1, it gives you a volume. Not the units, but the numerical answer. The units would still be in hypervolume, like quartic centimeters. But because you're integrating 1, it gives it the same numerical value as the actual volume. Maybe here's a good way to do it. Actually, I'm going to ignore this final bit of advice. Let's try to derive the volume of this, thinking about it as a double integral first. In fact, this is what the book does in the reading. They think about it with double integrals first, and then that leads them to triple integrals. Set up a double integral to give you the volume of the solid first. We could just integrate the top function minus the bottom function. What do I mean by that? The top function is the graph of this function of x and y, and the bottom function would be 0, whose graph is the xy plane. The bottom of this region here would be like a horizontal plane. Graph of z equals 0 would be the bottom of that region. So I'm effectively finding the volume between two functions of x and y, the bottom of which is trivial. How would you do that thinking about it with double integrals? In general, what you do to find volume between, I'll call it z equals f of xy and z equals g of xy, where say the graph of f of xy is above the graph of g of xy. That's the higher graph. And this is the lower one. I hope it makes some sense that you would do a double integral of their difference. F of xy minus g of xy over whatever region we're talking about. And here's how you relate this to triple integrals. Think of that inner difference of two functions as being an integral. Think of that inner difference there as being the integral of 1 from a lower limit of g of xy to an upper limit of f of xy. 1 is being integrated with respect to what? The other variable, z. And by thinking about it this way, which is, yes, granted, kind of strange to do this, you first of all are relating it to this idea of a triple integral with 3 integral signs. And secondly, it does emphasize that if we think of it this way, the inner integral is with respect to z. Does that match the directions of how to evaluate it? dz, dy, dx, yeah, the inner integral will be with respect to z. But how do you figure out the limits of integration on the two outer integrals? The same way we did with double integrals. Think about what the region R is. It's going to be a two-dimensional region. With respect to this picture, it's going to be the bottom triangle, the triangle on the bottom of the solid, which I can redraw in an ordinary XY plane. Careful though. I'm going to try to redraw that triangle in an ordinary XY plane. I got to be careful in thinking about it correctly though. X-axis, the positive x-axis is going to the left in this picture, and the positive y-axis is going this way. I got to imagine in my mind turning myself around and looking down on it effectively. This line is a line in the first quadrant. It's going to have a negative slope. Right on the sheet of paper, it looks like it has a positive slope. But if you imagine coming up over here and looking down on the XY plane, it would have a negative slope. Y-intercept at 1, x-intercept at 3. Y-intercept at 1, x-intercept at 3. It would be this line right here. And this triangle would be the region R. The directions say dy dx is the outer double integral. That means think of it as vertically simple. Think of it as between the graphs of two functions of x. One of them is y equals 0. And the other one would be y equals, what would it be? 1 minus x over 3. Right? Y-intercept of 1, slope of negative 1/3. So, to do this integral then, for the outer double integral, it's with respect to x. X goes from 0 to 3. Y goes from 0 to 1 minus x over 3. And then the most inner integral in this ultimately triple integral is again going to be from g of xy to f of xy of the function 1, dz, dy, dx, where f of xy and g of xy are in the original three-dimensional picture, the top function and the bottom. G of xy was 0. That's 0. F of xy was that function there. 2 minus 2x over 3 minus 2y. 2 minus 2x over 3 minus 2y. That's what we got to do to find the volume. But doing the inner integral is very easy. You just get the difference, f of xy minus g of xy. So it's like, well, why bother writing it as a triple integral? We'll come to that. But the inner integral we end up doing f of xy minus g of xy. When you integrate 1 dz, you get z. Z is getting evaluated between these two quantities. So you just plug this one into z and subtract what you get when you plug that one into z. This minus 0. You just get 2 minus 2/3 x minus 2y. And now just do the rest as a double integral. I'll have Mathematica do it. You've had enough practice by hand that you should realize this shouldn't be too hard to do. 0 to 3. 0 to 1 minus x over 3. Use parentheses. 2 minus 2x over 3 minus 2y. dy dx. Answer is 1 in the end. The volume of the solid is 1. But now, we do want to be able to set this up with respect to other orders and see that we get the same thing. Why? Well, one thing to know that you get the same thing is a good thing. Secondly, with harder examples, harder integrals, that you're not integrating one, but something else like a density function that could be complicated, maybe one of the other orders is easier than the initial ordering you're thinking about. You've experienced that with double integrals. Maybe one order is impossible, but the other order is easy. That can happen. So you want to have the skill to be able to rewrite these in other ways. How? Well, sort of with respect to the way we did it here, the trivial way to do it would be to think of this region as horizontally simple instead of vertically simple. Solve this equation for x. Negative x over 3 is y minus 1. So x is negative 3y plus 3. Thinking of it as horizontally simple. For any given y, x is going to go between 0 and negative 3y plus 3. Actually, let's also have Mathematica do this as triple integrals. I did it as a double integral here, but let's check what we did here as a triple integral as well. X goes from 0 to 3, y goes from 0 to 1 minus x over 3. That's the same, but I'm going to do a triple integral for the inner integral with respect to z. Z goes from 0 up to that graph, 0 up to 2 minus 2x over 3 minus 2y of the function 1. dz, dy, dx. That gives us 1. So the most trivial modification of this is to switch around the x and the y. To think of that two-dimensional bottom of the solid as being, when you look at it as an xy picture, it's horizontally simple. Y went from 0 to 1, and x went from 0 to negative 3y plus 3. So this should still be 1. It is. Okay, what are the harder ones? There's 4 more to go. The harder ones are ones where the integral is not with respect to z, but either x or y. How do you do that? Initially, I was thinking of this as being between the graphs of two functions of x and y, thinking of the xy plane as being the domain of these graphs, the slanted plane, and the xy plane itself, the bottom of the object. Alternatively, I could, for example, think of this slanted plane as being the graph of a function of y and z, sort of being above that plane, the plane of the paper, effectively. A function of x and z, excuse me. Y is a function of x and z. The back of that region would be the lower limit of the inner integral, and the top of that region in front of the object, the slanted plane, would be the top limit of that inner integral with respect to y. How would I figure out what that thing is? I'd have to solve this equation for y as a function of x and z. So if I solve that equation for y as a function of x and z, the equation is z equals 2 minus 2/3 x minus 2y. Solve for y. I'll add 2y to both sides and subtract z from both sides. And then divide both sides by 2. This same plane right there, the face of this object that is closest to you, has alternative function representations as a function of x and y, or now as a function of x and z. This would be what I'd do if the inner integral is done with respect to y. I'd want that integral to go from 0, which is representing the back of the solid, where y is 0, and this function here. That's the inner integral, but what about the outer integral, either dx dz or dz dx? I'd have to think about what happens. Well, where am I in it? What region am I integrating this over? If I smush this, the first way we did it, if you smush the solid down into the xy plane, you'd get this triangle at the bottom of the solid. On the other hand, if you smush it onto the xz plane, you get the back triangle. That would be the region, R. But be careful in how you look at it. To look at that correctly, draw it correctly in a two-dimensional plane, you'd have to imagine going behind the solid and looking at it from that direction. Or I guess since I'm up here, I should say from this direction. If I'm going to draw it and make the x-axis go this way and the positive z-axis go this way, I kind of have to imagine going back behind there. The z-intercept is 2, the x-intercept is 3. The region R now looks like this. It's not the exact same region in the xy plane as it is in the xz plane. That line has equation z equals 2 minus 2/3 x. As a vertically simple region in the xz plane, think of it as between the graphs of two functions of x. Your order would be dz dx, and x is going to go between 0 and 3, and z will go between 0 and 2 minus 2/3 x. X goes from 0 to 3. Z goes from 0 to 2 minus 2/3 x. Y still goes from 0 to 1 minus 1/3 x minus 1/2 z of 1 dy dz dx. 0 to 2 to 3, 0 to 2 minus 2x over 3, and 0 to 1 minus x over 3 minus z over 2. 1 dy dz dx. Should give us 1. Yes, thankful it does. Just to illustrate that you got to get it right. It's not just a coincidence. I bet if I switch the x and the z around here, well, yeah, it can't possibly work. Something goofy is going to happen. Yeah, it can't possibly work if I switch the x and the z around there. Even if in switching the x and the z around, even if I change this x to a, even if I change this x to a z, it still probably won't work. Okay, we got a number, but it's not the right answer. So you do got to get it right to get the right answer. Likewise, in this picture, I could think of it as horizontally simple. Solve this equation for x as a function of z. 2/3 x would be 2 minus z So x would be 3 minus 3 halves z. Isn't this fun? You can imagine how difficult these can get. The outer integral, okay, the outer integrals with respect to z now, z goes from 0 to 2. X goes from 0 to 3 minus 3 halves z. Limits of integration on y are still the same. And now it's dy, dx, dz. Still. There's 2 more to go. We're running low on time. Let's not actually do them, but just talk about how you do it. You'd have to think of this region as being between the graph of 2 functions of y and z. And your triangle for the double integral would be this triangle over here. Functions of y and z, so you'd have to solve this equation for x. The lower limit for the inner integral would still be 0 because the rightmost side of this object is where x equals 0. The upper limit would be still the same slanted side, but now as a function of y and z. And again, the two-dimensional outer double integral would be over this triangle in the yz plane. When do we not integrate 1? For example, when we've got a density function that's not constant. Delta of x, y, z. Well, we could say maybe we've got a density function here, and we'd like to know the mass of the solid. Maybe the density function is, 2x plus 3y plus 11z or something like that. The mass in that case would be 31 over 4. 7.75 grams if this density function were in grams per cubic centimeter. We could find moments and centers of mass. If we integrate x times the density, think three-dimensionally here, you got an x-axis. Let's say the x-axis is coming towards you, the y-axis this way, z-axis this way. You're integrating a density times x. X direction is perpendicular to the yz plane. Thinking about rotations gets confusing. The moment is called m sub yz. When you integrate x times the density, that's m sub yz when it gives me an answer. If I take that and divide by the mass, 31 over 4, that's giving me x bar, the center of mass in the x direction. These are in the book. 3 minutes. Oh boy. What would we do for an example, say, like this? Still different ways of thinking about it. You could think of this solid as being the solid between this graph up here and the bottom. Z goes from 0 up to this function. Okay, well, the equation of that is written y equals 1 minus z squared. But if I'm thinking of it as the solid between those 2 functions, I'm thinking of those as graphs of functions of x and y. Y minus equals 1 minus z squared is giving that surface as a function of y, or a function of z, and x effectively, where there's no x in there, though. It doesn't actually depend on x, though you could think of it as a function of x and z. Effectively as a graph over the xz plane, where the xz plane is effectively like the paper over here. If I wanted to think of it as a function of x and y, I'd have to solve for z. First, z squared would be 1 minus y, then z would be the square root of 1 minus y. And think of that as a function of x and y. So for the inner integral with respect to z, you'd go from 0 to square root of 1 minus y. That would be the inner integral with respect to z. The outer double integral over a region, well, region would be, it would be when you compress this thing down to the XY plane, it would be this region down at the bottom there, which is no longer a triangle, but a curved region. What's the graph of that curve? It's y equals 1 minus x squared. You could draw that in an XY plane to help you figure out how to represent R, either as vertically simple or horizontally simple.